Okay, again, welcome to the lab session of Monday. Today is September 28th. This is the last, basically the last lab of this month. Okay, so this is Lab 3, and it all has to do with Ohm's law, the law that we have seen earlier today. And basically, which is in the second version, which is the voltage is proportional to the current, V equals to Ri, where the constant of proportionality is the resistance. Granted, sometimes the resistance actually can be varied, and then the current or the voltage will change depending on which one is maintained. So you can keep one of the other parameters. So it's only basically three constants involved in it, three terms in it: the voltage, the current, and the resistance. The resistance is going to be in ohms. At some point, we're going to discuss a little bit of circuitry, which is we didn't cover yet in terms of the lecture, which is supposed to be of chapter 26. So what I'm going to be doing today is actually in the lab is to show that those expressions for the resistors in series and the resistors in parallel, they do make sense because you will need them for this circuit, okay, for this lab. So without any, let's get into the lab, okay? Is this the instructions? Let me check. Yep, these are the instructions. So let me change the view on my screen in here. Hopefully you guys already have the lab report form open for you guys and that you're looking at the same thing I'm looking at, okay? Again, let me stop sharing the screen because it's very important. I don't know how much I can emphasize on this. I know a lot of you are now being, basically they understand how the process works. So this is not a problem, but for some of you, it's probably still a kind of an ambiguous, a little bit of an issue. So I want you guys to come into this one. Okay, there is a problem already. This is not due the 29th. Is it due the 29th? October 6th, but the text in here does not reflect that, okay? So October 6th. Next Tuesday. When you see something like this one, please do send me a note, send me an email. I know this, and probably some of you now, they know exactly what's going on. They don't really pay attention to a lot of this text because they've been used to it. But let's make sure that it's clean. I know the lab in the bottom, it shows that it's due October 6th. So that was not the issue, but the text in here was showing the wrong date, okay? So we need to update this stuff in there too. Anyway, the lab instructions are in here. And very important, and that's why I'm in here actually, is to look at the syllabus. This is, the syllabus, I'm sorry, on the rubric. It tells you exactly how this thing is going graded. So you need to know what to do to get the full mark in here, okay? So there is only a couple of tables in this lab, okay? There is table 2, which is worth 12 points, and table 1, which is worth 56 points. That's the biggest part of the your grade. And the typical stuff for the questions there were 2 points, and the name, don't forget to put the other people who worked with you also in there too. That's worth 1 point. The 3 points for the objective, it has to be accurate, it has to be related to the topic, and it has to at least include 2 sentences or more. The conclusion is similar, connecting back to the objective and also including data to explain your answers to compare to the original one, and also 3 or more sentences. Everything else is systematic. So I want to bring your attention back to this one. I know this is the 3rd lab, so hopefully it's becoming a habit to you guys to go in there and do check mark, go through your lab before submitting it to make sure that you have everything that is supposed to be there is in there, okay? So in terms of the instructions, let me stop this one and go back to where we were in the PDF file. So this is Lab 3, as I said before, it's Ohm's Law, and Ohm's Law is really written in this format, okay? This is what we mean by Ohm's Law when we say that it's Ohm's Law. This is the one, okay? V equal to Ri or IR, where V is in volts, the current is in amps, and the resistance is in ohms. Again, we went through the derivation a few minutes ago through the lecture, basically, when we got the expression for the resistance in general for a wire of a specific shape. R is related to the resistivity, is related to the length of the wire, and it's inversely proportional to the cross-section. I already stated that this is Ohm's law, written J equals to E over rho, but don't forget some of the literature, they write actually sigma E, where sigma is just the inverse of rho. Conductivity, this is called the conductivity, and this is the resistivity, okay? So if rho is in ohm meter, the conductivity is 1 over ohm, 1 over meter. Okay, so that's basically what but most of the literature, most of the times, you will find everything is published in terms of rho, okay? By the way, we didn't talk about the effects of temperature in class, and that's something that we have to defer back to Wednesday. I remember I said that by Wednesday we'll finish these things, and then we will continue the next chapter. So we need to talk about the effects of temperature because the resistance changes with temperature, increases actually with temperature. That's why at some point there is a question in the bottom in here, all the way to the last question. Let me change this so that it can browse faster. What is the difference between ohmic resistor and a non-ohmic resistor? Is the one where the doesn't obey that relationship. P doesn't look like it's a linear function, it's off, okay? And that is usually because of heat. When the temperature starts to change, the resistance is no longer constant. So let's go back into the first expression. This is an ohmic resistor, V equals to Ri, okay? But if you let, and this, if we did actual lab, you will feel the heat coming from the resistor. And that is the power that we calculated already, Ri squared, okay? And that heat is energy coming from the resistor, and it increases its temperature, and the resistivity itself is a function of temperature. As the temperature increases, the resistance increases, and you will see the current decline. So instead of looking at something, I'm going to draw V, and this is the current I. So instead of seeing something like this, where it starts more or less from the origin, okay? Instead of seeing something like this, it's going something different completely, okay? Okay, I cannot do that. So it's going to decline over time, so it's not going to be linear, okay? It's not going to be a line. So that is the non-ohmic resistor, and this is the ohmic resistor, okay? The one that is linear. And usually the culprit in this case is the temperature. And you would see that in the actual lab. You would see actually the line is not exactly linear because of the effects of temperature if you let it stay for a long time. That's why they warn you a lot when you're doing this lab. You have to let it cool. You have to wait for it to cool down a little. And when you turn the voltage on from the power source, you do the voltage, you do the reading, you turn it off. You record the reading on your table, then you turn the power on again to read the next voltage. So we're changing the voltage. Let's say, for example, we start the voltage at 4 volt and we get all the way to 12 volt. By increments of 1, you put the 4 volt, you see the current, you turn it off, you record your data, you turn the back on, and so on and so forth until you get all of your data. Because if you do it, if you turn the voltage and then leave it at 4 volt, and then you go and record your data, then you change to 5 volt, you record your data, instead of seeing a line that is going to go straight between V and I, where the slope is actually the resistance, you're going to have a different line, a different curve. Actually, it's going to be a curve, not a line anymore. And that is because of the fact that R is no longer constant. The slope is not constant, okay? So that's something that you have, technically you have to be aware of when you're doing a lab. It's easy when you do theory, and it always works beautifully when you do theory, but when you're actually working in the lab, you have to pay attention to all of this fine-tuned details, okay? So that's one thing. Now, this is the thing I was going to talk to you that is part of chapter 26, but we will need it in today's lab. So we need to understand when we connect two resistors in series and when we connect two resistors in parallel, how they behave. This is opposite what the capacitors do. In the case of the capacitors, the equivalent capacitance in the case of series obeys the inverse law in a sense that 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3 and so on and so forth. And when they are parallel, the equivalent capacitor is just the sum of the capacitances. This one is the opposite. The resistor, when they're in series, the equivalent resistance is R1 plus R2 plus R3 and so on and so forth. So if you have a 10 ohm and a 5 ohm and a 7 ohm, when you combine them together, it's going to be 22 ohms, okay, in series. When you put them in parallel, it's going to be an expression that is a little bit involves a little bit of calculation. So that's why I'm putting my calculator in here. So I gave the example I gave the example of 10 and the example of 7, I believe, and the example of 5. So I have to add them up inversely, and then I have to invert the expression. This is the key thing in here, okay, to find a resistance of 2.2, which is smaller than even the smallest, okay? And that's typical because that's a property of the inverse. So let me stop sharing that screen and open a new tab in my notes to show this expression. So let me get into my notes in here. So this is in a sense part of chapter 26, which is going to be on Wednesday. So we're probably going to skip this discussion when it comes to Wednesday because we're going to do it today and it's needed for the lab, okay? So I have two resistors. I need to have my so I have R1, I have R2, and as you can clearly see they are in series. So what that means in series is if 10 coulomb every second pass through this here, that means 10 amperes. They will go through the resistor and they will emerge in here intact, 10 coulomb per second, which is 10 amperes. And they go through the second one unimpeded. So, I mean, impeded, but they will end up in the other side too. Okay, so that's conservation of charge. So I and I. So the current is the same. When I'm dealing with series circuits. Remember when we were talking about capacitors, we didn't have currents, we had charges. So it said the charge is the same in the case of the series for capacitors. Now it's the currents, because the currents and the charges are related to one another. All you need is just divide by time. So this is actually the conservation of charge still. So we said that it has to do with the conservation of charge, and here it's also the same thing, except this is charge per unit second, per unit time, which is coulombs per second. So it's the same thing. So now we have this expression for the current. For me, this looks like something, okay? This looks like I'm dealing with this circuit. So if I have a voltage difference between one end and the other, so if this is V1 and this is V2, okay? The difference in potential between the starting and the ending is just the sum of the two differential potentials. The same thing what we did in the case of capacitors. So I'm going to call this point 3, and I'm going to find V1 minus V3. I mean V1 minus V2, which is the actual difference in potential. That's what causes the current to start flowing, is equal to V1 minus V3 plus V3 minus V2. It's still the same thing. Now, V1 minus V3 is the potential across this resistor, the drop in potential across this resistor. And V3 minus V2 is the drop in potential. V3 is higher than V2, but must be less than V1. So if V1 is 10 volts and V2 is 2 volts, there is a difference of 8 volts difference between V1 and V2. But if V3 then must be somewhere in between them. V3 could be 5 volts, for example. So that's basically 10 minus 5 plus 5 minus 2 is going to be the same thing as 10 minus 2. So that's basically the algebra in terms of algebra. So this one, the drop in potential in the cross the R1 is just R1 times the current. That's Ohm's law. This one across the second one is R2 times the same current. And this looks like it's a big R, which is equivalent to both of them, times the same current. Because for my vantage point, I'm looking at a difference of potential V here between 1 and 2, where there are two resistors, and this they look like one big R equivalent. So in here, that's their sum. Of course, the I cancels from both sides. And they end up saying that my R equivalent in series is simply the sum of the R's. If I had 3, I'm going to add another one, and so on and so forth. Okay? So that is resistance in series. Now, when they're in parallel, it's a different story altogether. When they are in parallel, I have 0.1. I'm going to break it down into 2 now. And I have another resistor that is also in parallel with the initial resistor. And both of them are connected between the voltage difference, the same voltage difference, okay? If this is a 10 volt, 8 volt difference, this could be, for example, a 10 volt point, and this is a 2 volt point. The difference 10 minus 2 is still 8 volts. But that difference, since this has 0 resistance, that's a wire, it's the same in here. It's the same in here. It's the same voltage. Since this is R1 and this is R2. But the currents cannot be the same now. The same current I is split between I1 and I2. Okay? That's to comply with the conservation of charge. If 10 coulombs come in every second, probably 7 of them one way and 3 of them the other way. Okay? So that the sum of the two is still 10, the original number. So the current first, I, must be, the total current, is the sum of the two currents, I1 plus I2. And the voltage is the same. The voltage in here must obey V equals to R1 I1. That's Ohm's law. And the same V must be also equal to R2 I2. Okay? So I1 is V over R1, and I2 is V over R2, just by subbing the value from Ohm's law, okay, for I1 and I2. And this looks to me, since it's the same potential, V between 0.1 and 2, as if I have an R there, only a single R. These two are no longer there, as if I have only a big R equivalent, so that V equals to Ri, where I is the total current, R equivalent to I. So in this case, this I must be also V over R equivalent. Cancel the V from both sides, and the R equivalent in the case of the parallel is going to be the inverse of the sum of the inverses. 1 over R1 plus 1 over R2. If I have a third one, it's going to be 1 over R3 and so on and so forth. Okay? Don't forget, and this is the only caveat that I can only remind you, and I don't know how many times, but you have to remember it. The actual R equivalent is actually the inverse of the sum of the inverses. That means we have 1 over R1 plus 1 over R2 plus 1 over R3 and so on and so forth. When you're all done, you have to invert it one more time, okay, to get it in actual ohms. So you add the inverses, and then you inverse everything, okay? So now, this is the expression that is needed for the lab today. So I'm going to go back to the lab. So that's the justification. Again, it's coming from the lecture from chapter 26, because we're going to be doing the lab for it. Again, always defer the objective to the end. It's a good idea. So we're checking to do so the first thing we're going to do in here, and this is critical, okay, I'm going to click on the link. I'm not going to click anything after that. I'm going to stop sharing the screen and come back to it, okay, and follow the instructions. So I clicked on it. It opens the tab. So I'm stopping in here and I'm coming back to share the screen that I just opened. Okay, let me close everything in here because, oops, I didn't mean that. Okay, let me open a new tab in here because I have a bunch of things open in there. Okay, so let's do that one more time. Okay, where is the, so all I'm doing right now is clicking on that. And once we have it, let me share with you that screen so that you see it, okay? Share, here is the screen, okay? When you see this lab activities and they have this 5 next to them, that means it's safe to open them in HTML. They are HTML5 compliant. That's why I was telling you guys to get because some of these activities, they involve Java. So you need to download Java for the next lab because it's not translated to HTML5. Do not, and I try to avoid doing that at all with Flash. Okay, some of them are actually Flash, so I don't like to do those because actually my computer doesn't have Flash and it wants me to download it and enable it, and even still, it doesn't run. Okay, I know it's being completely deprecated, so it's useless now to do things with Flash. So you will need for the next lab Java, not JavaScript, Java. Okay, and this is. For this one, it's fine to do it with the HTML. So I'm going to click on it to see what opens. So the interactive simulations opens, and we don't do the intro. We go straight to the lab. Okay, we go to the lab. So double click on it to open it. Now we have the lab. Let me see exactly what is the lab look like. Okay. So the first thing first. In the lab, when you are there, what you need to do is change to this view. No, what is the view that we need to change? Yes, click on this one to change at least to the model, because I know it looks like a battery and it looks like a resistor, especially with the color-coded resistors and so on and so forth. But we're not going to do that. We're going to go straight to the symbolic representation. This is how the battery looks like. This is how a wire looks like, a light bulb looks like, a resistor looks like, and this is the switch that at some point we need to turn on things in there. This is a fuse. Again, what else do we need in here? Sometimes we will need capacitors. We don't have that for this lab, okay? This lab doesn't have that. So in this lab, we only have the devices that we have in hand. So let's go back into the instruction and basically see what's going on in here. Setup. The wire resistivity should be small, but not tiny. So the first thing I'm going to do is change the wire resistivity. Here is the wire resistivity. Should be small, but not tiny. Any number in here is fine, okay? As long as you move out of this thing in here. The battery resistance, it tells you to be around 1 ohm, okay? If you do 2 ohms, that's fine, but don't make it too big, okay? Because the actual resistance in here that we're dealing with in this lab are of the order of 5 ohms. So you don't want the battery to be too high, okay? So that's basically for this lab. So let's check the instructions again. The switch needs to be closed. So we're going to connect these things first, okay? So for my lab, I need a battery. I need a resistance. I need 2 resistance, actually. I need a switch. And I need also an ammeter. And I need also a voltmeter. So those are the things I'm looking at. So let me go back into where you guys are. I'm looking at the PDF file. So I need a battery. So I'm going to grab the battery, put it in here. I would need a resistor. I'm going to turn it around. Okay, in here. Make it vertical a little bit, okay? And then I need another resistor. I need a switch. I need, let's put this thing a little bit higher, okay? Because I need that voltmeter. So let's put this one a little bit higher. This one actually needs to be higher. If you want to delete something, there is the delete the button in the bottom, okay? I'm sorry, when you click on a device, the introduction comes in. So this resistor needs to be at 5. I'm going to drop it to 5 ohms, okay? I know that. This one has to be 12.5. We'll start with it. So again, we're going to make it 12.5 in here. Ohms. the switch right now, it's open. And one of the things, oh, we need to close, open it. And one of the things it tells you to do is change it to conventional. You don't need to be looking at electrons. Just look at the signal of the current in here, okay? We need to see the values in here to where we are. This battery needs to be at 120, which is the maximum in here, okay? And we need wires now. What else do we need? We need an ammeter. So I'm going to bring my ammeter and put it in here. And we need also a voltmeter. So here is the voltmeter. The voltmeter already is going to be reading the ends between this resistor. Right now it's looking at 0 volts, okay? That's fine. So we need wires now. We need to bring this wire, connect it in here, connect it in here. We need to have another wire, connect it in here, connect it somewhere in there. Okay, you can connect it straight out if you like. Okay, you don't need another wire. Connect this wire in here, this wire in there. Now we need to bring this wire, connect it in here, connect it in there. Another wire from here. If you like, you can connect it directly to the ammeter. And now the current reading is 0 amps. I know it doesn't look 100% like the one that you had before you, because I had extra wires in there, but that's fine. As long as your circuit look more or less like this one. Is the battery oriented correctly or not? Let me check in there, okay? Because I think the orientation of the battery matters. Let me check the lab. Because the current will matter which way it's flowing. Okay, it's fine. The battery looks fine. If not, then you just turn it around, okay? So just click in here, disconnect, click in here, disconnect, and take this battery and rotate it, okay? To make the current flow in the opposite direction. But if you do that, the voltage later on, everything will flow this way, okay? So that's not the case, so leave it the way it was. Which brings you to an important topic in here for later on, which is the polarity in there, okay? So we set up everything, aren't we? Did I miss anything in here? Okay. I have, okay, this resistance is going to be called RE, the rheostat. Let me go back into your, so this is fixed at 5 ohms. This does not change. This one, you change it by basically going down in the bottom and changing its value, okay? So at some point, you're going to collect 6 data. So try to get 1, 2, 3, 4, 5, 6 data, for example. It doesn't have to be something, as long as you start from 12.5, your base, and then you can put any 6 data is fine in here, okay? You're supposed to see, in practice, if you're going to do that, you're going to open and close the circuit while you're doing that, okay? So you have to be careful, because you're actually changing the resistance. There is, I mean, unless you have those ones that dial, yes, you can change it on the dial. That's fine, okay? But that's basically how you do that. But in practice, at least in the labs that I've done in the past, we have different various batteries, and usually we have about 4 or 5 I've seen. I don't think that I have seen 6 different values. We change them and put the other one, disconnect, put the other one, disconnect, and so on and so forth, and checking Ohm's law in this case, okay? And sometimes you can get more values by just combining in series more and less and things like that. So that's basically how you're, you get them less by combining them in parallel, you get them more by combining them in series. So a 5 ohm and a 5 ohm will end up in 10 ohms if they're in series, or 2.5 ohms if they're in parallel, okay? So depending on how you want them. So in this case, you will have 2.5 and a 5 and a 10. Okay, so for just with 3 batteries, you have 3. With 2 resistors, you have 3 values basically that you can play with. Okay. So let's continue the discussion in here. See what's. So we did that. We did the 120. We did. Now measure the voltage across V1 side and drag it to, okay, we did that. Click the ammeter and place in the side. Vary the rheostat to obtain 6 values. So we're going to close the circuit now. I'm sorry, close the switch now, because at this point, what happened? Are you still looking at the picture of this thing or not? circuit online? And you should have yours open too. Yes or no? I need feedback from you guys. Very hard to teach class with no feedback. Are you looking at the circuit? Or not? Yes or no? Eric, Israel, Sebastian, Braxton, Jose. Okay, right now, no. How about now? How about now? Thank you, Sebastian. Okay, very good. So, thank you, Braxton, Israel, too. Okay, very good. So we're in good shape then. So we're gonna close the switch, and you will see the current flowing through the ammeter, okay? And also the voltmeter now starts to read values in there. So we're going to close it now just by clicking on it. So the ammeter is reading 6.16 amps. Remember, the voltage is a huge 140 volts, and the two resistors combined, they add up to what, 17.5 volts, 17.5 ohms. I'm sorry. So that's why there is that much. There is already a 30.78 volts drop across this one. So I'm going to stop this one quickly. I mean, I will write these numbers first. I will write 6.16 amps for the current, and I'm gonna write 30.78 for my voltage. And I'm going to stop sharing the screen and go into my PDF file, okay? Share. Vary the rheostat to obtain 6 different values and the corresponding values of the voltage V. Then record data on the table 1. So here is table 1. We have to actually, the voltage on R1 is 30.78. The current is 6.16, I think, 30.78, and this is 1. Now, I need to find, I know what the current is also on the same resistor, but I need to find what the voltage across the second capacitor, second resistor is. I'm going to stop sharing the screen and go back into the same thing in here. Unfortunately, I don't have another voltmeter, so I'm going to use the same voltmeter. Look, this is a technique I'm going to do for this one so that quickly I can go through this one, and this is what I would do actually in the lab. Instead of moving the entire voltmeter, since this point is the same point on the entire voltmeter, I'm going to leave the red end, the positive side on one side, and I'm going to bring this one. So the number is going to be negative now, okay? So when I'm reporting it on the table, I'm going to put it positive. If you don't like that, that's fine. You do this, and you connect it in here, and it should be the positive value in here. It's not connected. It's not connected on this end, okay? So right now it's reading 76.95 on V2. Does everybody understand what I'm doing in here? So this is the negative. This is the cathode. It goes in here. This is the anode, goes in there. So right now I have V1. I have V2. And this is both of them together, V1 and V2. Okay, if I'm really interested in that. So I need all of this data. Okay, let me stop sharing. Oops, yeah, stop sharing that screen and go back into my PDF file. So now connect R1. Okay, so we're going to do a different data first of all. Vary RE 6 different value, then connect it, okay? So we're gonna get this 6 data, 1, 2, 3, 4, 5, until we get all of these things in here, okay? Oh, no, I'm sorry, I'm in step 2. I'm step 2, sorry. We're still here, okay, step 2. So we're varying for 6 different values again. Replace R1 by R2 as shown below, equals to 10 ohms. Alternatively, you can, oh, I'm sorry. I'm completely sorry. You just need the first column. That's it, okay? So this table is kind of a little bit misleading you, okay? So please, so the first recording, don't move the voltmeter. Don't leave it where it was, okay? Let me go back. So you do the first reading at 12 ohms. I'm gonna come back in here. I'm gonna change the value in there. The current will change, and so the voltage. So I'm gonna put a different value. When I change that, the current dropped and the voltage dropped because I increased this resistance now, the rheostat, okay? So I have new voltage, a new current. I plot them on the first 2 columns, the current for R1 and the current for R2. Now I do the same thing, a new value. Now I have a new value for the voltage and a new value for the current. Of course, the current now is a lot less, 2.3 amps, okay? And the voltage now is less because I'm increasing this resistance. So there is a huge drop in this resistance now. I'm gonna increase a new value, okay? The voltage has dropped further, the current has dropped more. So I'm gonna increase this resistance more, okay? Now I have a new value for the voltage and the current is extremely slow now, as you can see from this animation. Until I get 6th value. So the maximum I can go is 180 amps. And at that point, the voltage dropped a lot and the current is 0.94. Is this clear? So we're done with step 2 now. Let me stop and go back to sharing the screen. So step 2 now, you don't change R1, keep R1 the same. Change R2 and record the data in the first 2 columns, okay? Now, step 2, we're done with it, okay? Oh man, this is, okay? This step now, okay, I need to change the labels in there. This step now, we're gonna change the value of R2 from 5 ohms to 10 ohms. And repeat the same thing, basically. So now we're gonna go back to a small value in here, or we can keep it big and come down to it, it doesn't matter. But it's a good idea to probably bring this one down to 12.5 ohms. 12.5 ohms. Now we need to change this resistor to 10 ohms, double the value now, okay? And repeat the same process as before. Repeat the same process as before by varying this resistor between 2, 3, 4, 5, 6 readings, okay? 6 readings, and each time you record the value of the voltage and the value of the resistor. You should find lines. In either case, you should find lines, okay? Between the current and the voltage. The current, remember, is throughout the entire circuit. And the voltage across just the resistor that you're looking at. Let me go back into the instructions in here. The next step is vary the rheostat to obtain 60. So that's, we did that. Now connect R1 and R2 in series. So basically the same lab, except now we're doing them both in series. So I'm already sharing that screen. I'm not here yet, so let me go back into it. So now this, let's keep them the same naming. This one needs to be 5. I know it's not a real lab to do in the lab where you actually change. So I'm going to open the, technically we're supposed to open this, and if we are really doing it in lab, okay? Because this thing is heating a lot by now. And this is 10, okay? So now this is the step that I was talking to you earlier. This The current, you don't change it, you leave it there. So I'm going to open this one in here. So the current, now I have a 10 and a 5, so it's 7.06, okay? And I'm going to measure the voltage across both of them, okay? From end to end. It's 107 volts drop from the first resistor, which is 10 ohms, to the 5 ohm resistor. Let's see here, what are we changing in here? Okay, I'm sorry. We need to add another resistor. This is no good. Let's open this one in here. We need to have this one in there. Okay, now this is the two resistors in series, okay? And this one needs to start at 12.5. Let me move this out of the way. Put it 12.5. This is to control the current, really, okay? So now, and this one needs to be here. So now we have the 2 and the 5 and the 10 in series. So we're gonna connect this circuit and now read the current in here, okay? Change this value to 1, 2, 3, I'm sorry, 1, 2, 3, 4, 5, and probably somewhere a 6 value in there, okay? And each time you record the data. They're in series. Now stop this one for the last part of the lab. Let's open this circuit in here. We're gonna take, let me remove the voltmeter from it. Remove this to disconnect here. Disconnect here. Disconnect from this point and disconnect from this point. I'm going to take the 5 ohms. Let me just throw this thing away. This point, probably I don't need it. I will need something else instead. Bring the 5 ohms. They are now in this. They are, and so connect one of them. Connect the other one. And these 2 points, they need to be connected now. Now they're in series. I mean, they're in parallel. Okay, the voltmeter now doesn't matter. I'm going to put them in here. So it should be reading the same voltage across both of them. Okay, and the same thing now, close the circuit. Now vary. Let me start back with the 12.5. Okay, do the first reading. And let me move this. And this is 1. This is 2. This is 3. This is 4. This is 5. This is 6 readings. Each time I'm reading the actual current and the resistance. The current is by the ammeter on the top, and the voltmeter is in here. As long as they have the 2 resistors, this is the current that comes in there, and it's split up in 2 ways. If I'm interested trying to find what that current is, so let me break my circuit a little bit in here. Let me open the switch. Let me remove this connection. Let me remove that connection in here. And let me put this wire out of the way, this wire out of the way, and this wire out of the way. Okay. What I can do in here is I can bring another ammeter and put it in here, and another ammeter and put it in here. Okay. And connect these 2. And now I would have the actual, oops, sorry. It's fine. Okay. I will have a reading of 2 different currents that they should add up, 0.83 amps and 0.4 amps, 0.43 amps, they should add up by the conservation of charge to 1.26 amps. So this is the current through where the node has opened, okay? Make sure that I didn't miss any of the instructions in here. So let's look at the tables. You don't need those two ammeters because all you need is the overall amps and the overall voltage for the series. And the voltage is like I showed earlier between the two end-to-end resistors in series. And the same thing for the parallel. You don't need those individual currents. But it's a good idea to check, to do it on your spare time, to play with it, to verify that it still works in terms of Ohm's law, that the currents actually add up and the voltages are the same in the case of the parallel. Whereas the voltages add up, and I didn't do that, although we could have easily added the numbers in here. Let me share that screen and let me delete some of the things. Let me open the circuit in here quickly. Let me delete that. Let me delete this. Let's delete this wire. Delete this wire. Oops. Let's break the junction. We don't need this. Delete that. Let's put them back to the way they were in series, okay? So I could have found the voltage across both of them, which is 17.14. But if I calculate this one is 11.37. So I could what was the number? 17.14. Subtract from it 11.37. It should be 6 point something, okay? So they should add up to 17 point. So what is it? 5.62 plus. Oh, because you have the resistor, the wires, they have their own resistance. So there is a small drop in between them too, because this is actually simulating more realistic things. So they are nothing, but they should add up very close from it because this resistor is very small. So 70, this is from end to end 17. From here is actually slightly less because I have that extra wires. From here it should be less because I have that extra wire. Now I have 16.82. It should be the sum of 11.21 plus 5.61. So it's very close from the sum, and the error has to do with the wiring basically, and that's typical. Even in real lab you will have that. You would not, even in the case of the currents, they should not add up exactly, okay? Because of the fact that wires bring their own resistance and they would make those laws. But in an ideal situation where all of this resistance is zero and the batteries are ideal and everything else, everything should add up correctly. Okay? To the questions. Any questions so far before I go into the questions? It's straightforward, honestly. A lot of these labs, they're just basically making sure you connect them right and you put the correct ammeters. And here is the averages, okay? Because some of these questions, they are related to the average. So the first thing in this question in here was the average. Then based on the average is Ohm's law verified. Namely, this R, which was 5 ohms times this current I, is it equal to this voltage? The same thing, this I times the 10 ohms, is it equal to this voltage? The same thing now. This I times the sum of the 10 plus 5, is it equal to this voltage? And now you have to find the inverse, okay, which is this R equivalent, okay? And then you multiply by, does it work? Does it show you that this thing is working? So that basically depends on your calculation. And check this to see if any discrepancy is there, okay? In other words, if you take the ratio of this volt over this current, would you find 5 or a little bit off, okay? And how off is it from the 5 ohms? So that's basically what this question is. Question 2, calculate the R equivalent for the series and parallel configuration. So this question is actually, first one has to do with this 2, with this 3, basically with 2 resistors. And the second question has to do with this part. Both of these 2 questions should be straightforward. Again, you calculate R equivalent, which is just the sum of the R's. and you take this voltage divided by that current, and it should be equal to the sum of the two resistors. And then here you calculate the inverse of the sum of the inverses. And is this voltage over that current equal to that inverse of the sum of the inverses for the case of the series? I mean parallel. So those are the two questions. Then you're going to graph 4 graphs. You're going to graph this voltage as a this current as a function of this voltage, and the same thing everywhere in there, and the slopes should be 1 over resistances. Okay, for the graphs, or V versus I, the slopes should be the resistances. The V versus I and the slopes should be R equivalents for the series and the parallel. So we need 4 graphs total, 2 per sheet, 2 per the 2 resistors and the 2 equivalents. And do the best fits past the by the origin, because remember, V equal to Ri, when the current is 0, the voltage is 0. So do you get the line passing by the origin? If it doesn't, what does this mean? Okay, you're off by a little bit, and that's typical also. You could be off. Then again, you're taking the data from the previous tables, from the graphs. You're going to get the slope from the graph. You're going to get the second slope from the second graph. You're going to get the R equivalent from the slope of the third graph, and you're going to get the R equivalent from the slope of the fourth graph. You're going to compare them to what you know from the experiment. This was 5, this was 10, this should be 15, and this is 1 over 5 plus 1 over 10 inverted. So it should be 1 over what? 1 over 5 plus 1 over... It should be less than the smallest value, which is 10. .33 ohms. Okay, 3 1/3 of an ohm, which is less than the smallest of the values. And then you can compute the difference between them, and you divide by the by this one. Okay, and you multiply by 100 to find the errors. Again, I explained the ohmic resistor is the one that obeys V equal to Ri. Okay, non-ohmic resistors is when actually this is not linear anymore. It has a nonlinear effect. And in looking back at your graphs, do you think that your resistors behaved ohmically or not? They should, because there is no effects of temperature in here. If they do, they don't, then probably this simulation simulates more realistic cases than what these things are. And the conclusion, basically based on your errors, how much errors, how off are you from Ohm's law, and do the cases for the parallel and series connections also hold true for the circuits. Any questions? If no, you guys should be good on your lab. If you have any questions, please ask me, okay? So I'm going to stop the recording first.